Welcome, everybody. Welcome to those here with us in Bristol physically, and welcome to those dialing in online for this lecture. I'm Professor Phil Taylor. I'm the Pro Vice-Chancellor for Research and Enterprise here at the University of Bristol, and I'm absolutely delighted to be able to introduce this inaugural lecture. So this inaugural lecture is going to be delivered by Karen Aplin, who is a Professor of Space Science and Technology. And she really truly is an inspirational academic, and she's working in a fascinating interdisciplinary area, and we're all going to hear about that tonight, which is wonderful. She's a truly world-leading researcher, and I'm really proud that she's a professor here at the University of Bristol, making breakthroughs and real impact. Her lecture today is entitled, "Is the Atmosphere Electric? Investigating planets, ionization and lightning." And I think one key thing to take note of here is that Karen has developed a new area of science of planetary atmospheric electricity. And she's been recognized for that with the award of the James Dungy Lectureship by the Royal Astronomical Society. So we're really, really lucky to have Karen here, and I look forward to listening. Over to you, Karen. Thank you very much.
Thank you very much. Is the mic working all right? Yeah, cool. Right, it's lovely to be here. I was saying earlier, I don't think I've ever given a talk to such a mixed audience, like from my parents, my colleagues, and school friends, people, all sorts of different people. And that would be, I hope you enjoy it. It was interesting and fun to prepare it, something up for everyone, I hope. I can make this advance. Right, so I'm told it is customary to give a bit of intro to yourself in an inaugural lecture, something I wouldn't normally do. So I'll tell you a little bit about me to start with. I was quite a curious and geeky person, possibly still am. And I was interested in a lot of things, and I still am. When I was a child, space, it was Halley's Comet, it was the 1980s, and Voyager missions, they were really special. And the environment, of course, weather and that sort of thing as well. It all links up as you'll hear in my lecture. But I got interested in all those sorts of things. Of course, at that time, I didn't understand that they could all be linked. So, yeah, and I like my gadgets. And actually, I've got a gadget here, a prop. So, yeah, when I was a kid, I had a little thing called Little Professor, which is a children's maths game. And that was my first, I liked it very much. Used to play it under the bedclothes, and I was meant to be asleep. And that's my first encounter with what a professor was, 1980s maths game. And yeah, interested in space. I like to think I've got a little bit better at understanding space instruments and things since that time. So yeah, and then I actually came to Bristol for a work experience when I was about 16 or 17, and I did some work in the physics department about planets, and I really enjoyed that. It was really fantastic. I think I helped a professor prepare some schools stuff. But actually, I turned down an offer from Bristol, and in the end I went to Durham, and I ended up doing applied physics with some philosophy and history of science on the side, which I very much recommend as an option. So after I left Durham, I did a PhD at Reading University in the meteorology department. I made instrumentation to measure ionization in the atmosphere, which you'll hear more about later. And also I love music, and I played double bass since I was about 12. This has always been a big part of my life. And in Reading meteorology department, we had our own little orchestra, which is called the Random Ensemble. And that was the sounds it made quite often as well. So that's some of the things I got up to. After that, I went to work at RAL Space near Oxford as a researcher. And then I moved to Oxford University for some years. There's a very nice picture of Oxford. As many of you who work in science and engineering will know, there are lovely old buildings, and you can work in the basement of the concrete building. And that's what I did. And then I came to Bristol. So another traditional engineering building. So yeah, I came to Bristol in 2018. So what am I going to talk about today? Lightning. And then moving on from lightning, there's other forms of electricity in the air and how we can exploit those. And then there's you can have a linkage between lightning and other electrical phenomena in the atmosphere. And then I'll wrap up with some conclusions, and there'll be an opportunity to ask questions at the end. As it's the 4th of July today, I couldn't resist putting this picture up. which is not me running for president, giving a talk in the States at the Electrostatic Society of America. And in America, they're very proud of Benjamin Franklin, who did a lot of work on lightning and was also one of the founding fathers of the USA. So that's something to note for today. It's just fluke that this lecture's on the 4th of July, but that was something to talk about. Okay, so lightning. What is lightning? Lightning is an electrical breakdown of a gas. So if you have a gas and you have like too much electricity in it, a voltage builds up in the gas. If that exceeds a sort of limit to the gas, you get a spark. And that's lightning. You'll all have seen lightning. It's a spark in the sky. And there are other types of lightning which are related, which are things technically called glow discharge. You can get little glows and a whole range of different lightning phenomena, some of which I'll show you in a minute. St. Elmo's fire is the name for a glow discharge. You might have heard of it coming, from ships. It's a sort of model of an old sailing ship, and there's going to be a thunderstorm and you get a weird glow on the mast of the ship and people are worried, and that they should be worried actually, because there is going to be lightning probably if you get St. Elmo's fire. We know lightning's been around for a really long time because there are fossilized lightning strikes called fulgurites in sand and rock. The most famous examples are on Arran, and you can go and see them on Goat Fell. And they show, because the rocks are really old, that shows that lightning's really old. It's been around a really long time. And that was famously identified in the 1960s. More recently, lightning can strike things like brickworks. I think it was a brickworks with like a big pile of sand and the lightning struck it. And you've got one of these, you know that that's what lightning does. And there are labs in the UK now that actually make these fulgurites just for fun normally, but they're lightning labs. Lightning is generated by processes in clouds normally, and you need to have a mixture of phases. When we say phases, we mean ice, water, liquid water, and sort of hail and snow. And basically these, in a thundercloud, you have a lot of activity, sort of build up, turbulence, convection. Thunderclouds get very tall and the particles collide, and electricity is transferred from one type of particle to another when they collide. And so you end up with, mainly in thunderclouds on Earth, you have ice crystals, which end up being one sign. So they all end up being one way around. And then graupel, which is a special soft hail, is the other sign. And then the lightning, the ice sort of wafts up to the top of the cloud and the hail goes down. And that means you get a separation, you get a voltage building up in the cloud. And when that gets too great, you have lightning. In the real world, it's much more complicated. There's all sorts of different, the pluses and minuses can be in all different places. But that's roughly how it works. And you can have lightning from cloud to the ground, from one cloud to another cloud, from inside one cloud. So there's a whole variety of different types of lightning and ways that can work. So I've got some Earth examples here. I'll start on the right. No, I won't. I'll start up here. This is a video from Alec Bennett, who's here today. And I think this shows some lightning inside clouds. This is just locally in the West Country. And I think there's a cloud to ground strike at the end. So that's the lightning you'll have seen. We had quite a lot of a few weeks ago. On the right, this actually shows two types of lightning. At the bottom here, you can see some lightning in the thunderclouds. And you can also see this red glow here is a relatively newly discovered type of lightning called a red sprite. And it goes from above the thundercloud to the top of the atmosphere. And there's a whole family of these upper atmosphere discharges, but they're very, very beautiful and transient. And we have some photos of them. Another interesting type of lightning is volcanic lightning. This is generated in ash clouds from volcanoes, and it's the same sort of mechanism as I was just saying about for the thunderclouds. Basically, the ash will rub together and become charged. And then you get some of the ash rising because there's a big plume. And occasionally the ash can kind of mix with a normal cloud, if you like, and make an even more intense storm. This is a bit rarer. It's quite fun to watch this video. So that's at the top of the plume. So there's quite a lot of activity in that. So that's lightning in dust. You don't need water necessarily to have lightning. So lightning, nice to look at. But why is it important? I mean, it's a hazard. It can cause damage when it strikes things in space. It could damage your lander. And before you get lightning, you get electrostatic charge on things. And this means that things get sticky. So the dust, for example, could get charged and it sticks to your solar cell. It means you don't have enough power. So that could be a problem. Obviously, if you're sending people to space, you need to worry about them being in the way of potential lightning. Lightning also has a role to play in chemistry. And there's a very famous experiment in the 1950s by two scientists called Miller and Urey. And they had a kind of a tank, and they put some stuff in the tank that was the same as what was on the Earth billions of years ago when the Earth's atmosphere started. And they put some sparks through the tank, and they found that amino acids were formed, which are really important for life. And lightning also has chemical effects because it's very hot and very energetic. It can change chemistry, and it can affect nitrogen on Earth, which is important for agriculture and life. And it does things in other planetary atmospheres as well. We have a picture of Stanley Miller here. I think this is much more recent. He looks like a man who's had his photo taken one too many times. I think he was very young in the 1950s, and this was 10 or 20 years ago. And also lightning is obviously a weather phenomenon. And if you have lightning, that means you have severe weather. It means you have this process called convection, the mixing that forms thunderclouds. So if you're not able to see a thundercloud easily, if you see lightning, you know there must be a thundercloud. And this means also you need to have particular types of cloud to get lightning. So it's not just any old cloud, it's a special type of cloud, and special activity is happening to generate the lightning that you see. So how do we detect lightning? Well, there's a flash. You've seen the pictures already, and that is because the channel of air that the lightning bolt passes through, it gets very hot and it emits light. And what we find is that particular gases will emit light when they're struck by lightning, particular colors. And if you have a spacecraft and you want to detect lightning, you look at a particular chunk of this light, because if you just had just a normal camera, if you like, it could be a reflection from the sun, any old thing. So just get rid of that. So spacecraft lightning detectors tend to have filters that look in a particular portion of the light. And how do we know where to look? Well, for Earth, it's relatively easy because we know what gases are in our atmosphere, and we can see what we can measure from lightning itself, what happens. If you want to make a lightning camera for another planet, you need to have some idea of what to look for. And this is based on lab experiments. In particular, there's only really one set of lab experiments actually from the 1980s. Unfortunately, for the timing of this lecture, Europe has just launched a lightning camera on a spacecraft, a EUMETSAT, European Meteorological Satellite. And it's just started sending back data just in the last few weeks. And it's got some really nice pictures. So I've got a little video of this new data. So there've been satellite observations of lightning for about 25 years, but they've only been American NASA missions. And they focused on the orbit of the spacecraft, has looked at the USA because that's what they care about, and the tropics. And so this European lightning camera is the first one to focus on Europe and Africa and Asia. So here are some thunderstorms. This is the UK, if you can see. So it's sort of looking, that's Spain, and that's France, and that's the UK, and Ireland is here. And you can see this is a 12-hour footage from a couple of weeks ago, speeded up, and this is what it sees. So it's got really lovely lightning imagery, and you can deduce all sorts of stuff about what is going on with lightning from this sort of satellite data. And you can use it to improve weather forecasts and therefore hazards, lightning hazards and things like that, people will understand better. Now, I mentioned the sort of chunks of light that these special cameras look at. You might be interested to see that if you look at the color, because different wavelengths of light correspond to different colors. If you look at the particular chunk of light that is looked at for lightning cameras to look at Earth, and if you had one Venus and Mars, it's actually red light. It's not kind of yellow or white as you might expect, but that's the strongest, one of the strongest emissions from the gases that we have in Earth's atmosphere. So if you wanted to make a lightning camera for, let's say, Jupiter, it would be different because Jupiter has got hydrogen and helium in its atmosphere and not nitrogen and oxygen and carbon dioxide like Earth and Venus and Mars. So if you were to make a lightning camera for Jupiter or Saturn, and you made a filter for your camera, it would look at this bright red light, which is weird because it's not where you expect there to be a strong signal from lightning, but there is. Okay. How else do we measure lightning? Well, lightning makes crackles on radios, old school radios, not internet radios. So you can hear lightning on the radio. If you detune a radio during a thunderstorm, you can hear the lightning strikes coming through. And that's because lightning emits radio waves, and the channel where the current flows acts as an antenna for those radio waves. So if you have lightning on different planets, it's slightly different everywhere. It's sort of fundamentally the same phenomenon, but it behaves slightly differently. So if you have a shorter lightning bolt, it will emit a different wavelengths of radio. So you'd have to tune your dial to a different place to hear it than longer channels. And also you need to know how far the signal goes. That's related to how you might measure it, because if it doesn't go very far, you have to be close and so on. And the distance the signal travels depends on the frequency, the kind of radio tuning dial. And this is a slightly technical graph, but I will attempt to explain some of it. This is on the bottom of the graph, it says frequency. That is the same as your radio tuning dial, the frequency. And then this is the strength of the signal that you would detect at Earth. That's very small, it's very weak. And there's various stuff emitted by the sun and Jupiter and Saturn and things. But what happens is it's actually possible to detect lightning from Saturn at Earth by its radio emissions. And Uranus lightning is also thought to be not that much weaker. And Saturn lightning has been detected from Earth with a radio telescope. So there's a possibility of detecting lightning at Uranus from Earth as well. The trouble is, Earth emits radio emissions. I mean, we all emit radio and stuff as well, but there's a layer in the top of the atmosphere called the ionosphere, and those radio signals from space can't get through it to Earth. So if you're literally sitting on Earth's surface, if you have a radio telescope, you can only actually see that bit of the emission. So it's quite hard, but it has been done. It's possible to detect the Saturn lightning from Earth. And as a sort of side point, that is one of the reasons why having like a space telescope is better for this sort of thing, because you're away from Earth's atmosphere, and the principle for optical telescopes and so on. That's why we have telescopes in space that are used to look at signals from space, from galaxies and stuff like that. So there's another possibility for lightning detection, which is something to do with the signals that are excited inside Earth's atmosphere. So I mentioned there is a layer at the top of the atmosphere called the ionosphere that conducts electricity, and there's a surface we're standing on that conducts electricity, and the air doesn't conduct electricity very well. And if you have lightning strikes, that sets a kind of ringing in this gap between the surface and the ionosphere, and it's very low frequency. It's called the Schumann resonance, and that is another way that you could possibly detect lightning. So moving now to I've just got a couple of asides, because they're always sort of side things you do, and it's nice to talk about those as well. So one of my asides is about science and music. And as I've said, I like music very much, and you can hear music everywhere. And one of the first places I noticed that there was music, well, weather and music were linked. I played in an orchestra, and there were sounds that we were playing that were meant to represent the weather. And much later on, I did some work with some colleagues, and we looked at all the pieces, pop music and classical music that had weather in them, and wrote a kind of lighter style article for a magazine called Weather. And this was good fun, and slightly surprising, the media really loved it. So there's all sorts of media stuff about this, and I was on Radio 3 and Radio 4, and we were on Canadian TV and stuff. So if you want to look, there's lots of things on the internet about that. So that was a kind of fun thing that we did. And I like to think we actually counted up. It wasn't just like, oh, hey, there's weather and music. We actually tried to do it properly as scientists. So we sort of counted up the different types of weather and drew graphs of them and stuff like that, and tried to do some analysis. So that was a kind of fun side thing. And it's good. It explains to people. I mean, doing these things I was speaking to a general audience here, but I think it's important for scientists and engineers to communicate what they're doing more broadly than just to other technical people. And this turned out to be a really good way of sort of getting through to people that weather and climate are important. And also you can think about weather, music and lightning in different ways. So I just talked about the Schumann resonance, which was this low frequency sound, if you like, that's made by lightning in Earth's atmosphere. Now, it turns out there's a composer you may have heard of called Robert Schumann. That's a picture of him from 1850. It's not him. Schumann, who did the Schumann resonance, was called Winfried. And he predicted it, I think, in the 1930s or 40s, and it was detected in the 1950s. And this was particularly interesting to me because, as I've said, I play the double bass, and it's quite a low instrument. And this is a low frequency resonance. And I thought, aha, I can link these things up. And I am indeed going to link them up for you now by playing the double bass. So what I should say first is that the notes that the lightning makes are very, very low. They're so low you could never hear them. So I've made them higher to play on the double bass, even though the double bass is really low. The lightning notes are much lower. And also I've kind of converted them so they make proper notes. Otherwise it wouldn't sound nice. And it'd be very hard for me to play because, you know, we have notes that correspond. So it's the frequencies that correspond to notes. So I'm going to play notes. So I'll tell you first. So this is I'll just take that off there. So I'll show you how much I made them higher. So what I did, I made them 2 octaves higher. If you don't know anything about music, 1 octave is doubling the frequency. So I have a really low note here. And then 1 octave higher, something like this. So that's the same note. It sounds like the same note, but it's higher. And then we go higher again. So that's how much higher I made notes in order to sort of represent this lightning. And then, so there are different sets of frequencies that the different planets make. For Earth, we can measure them. They haven't been measured at the planets, but they've been predicted. So I've got the ones for Earth here. So there's a set of them. I think there's about 5 notes. So I'm just going to play these notes to you. So those are the notes that correspond to these lightning resonances on Earth. And then the way that the notes go is that if you have a smaller planet, the notes are higher. And on Mars, Schumann resonances have been predicted there because, as I will say a bit later, we expect there to be lightning on Mars. So we expect to hear these if we listen for them on Mars. And because Mars is a little bit smaller than Earth, the notes are higher. So I've got some higher notes here which represent the resonances on Mars. So that's what we expect these resonances to be like at Mars, although I don't think we've listened for them yet. I'd like very much for us to do that. So moving on, I was just playing you some notes from lightning. We can listen to lightning in more straightforward ways than playing double bass, you'll be pleased to learn. And one of these is quite obvious, it's thunder. And that is a pressure wave formed by the air. So the air gets heated, and it sets up a kind of vibration in the air, and sounds are vibrations in the air. So that is how we hear thunder. It's only detectable relatively near to the storm. So if you think about hearing thunder, I don't know if you look, you hear thunder and maybe look to see on the internet where the lightning storm is. It's usually less than about, I don't know, 40 miles away. How far the thunder sound can get depends on what planet you're on. And so on Saturn's moon Titan, which has a nice thick atmosphere, we expect the thunder sound to propagate a long way. On Mars, the atmosphere is quite thin, so there would be thunder, but you would only hear it nearer the storm. You might be interested to know that what we call thunder days are still the official way to record the amount of thunder we have on Earth. So we have satellites, but weather records are thunder days. And that is, there are observatories where the weather is measured. And if the person who works at the observatory hears thunder one day, they kind of write down Thunder Day. And that is the long-term record. I mean, it's good in some ways because it's been going like that for a long time. So we can see how lightning has changed. But it perhaps in some ways is a bit strange when we have all sorts of clever instruments that people make that thunder, somebody go, oh yeah, I heard thunder, is the still official way for doing it. You can also get lightning, it sort of propagates magnetic signals. So lightning, Earth's got a magnetic field. That means it's a bit like a magnet. If you've ever seen pictures, you remember from school, if you're not technical about like iron filings from a magnet, they sort of come out like that, the magnetic field, and that is the magnetic field of Earth. So it's just got a bar magnet inside it. And lightning tends to send signals along these magnetic field lines out into space. So if you've got a spacecraft, you can listen for these. And I have a video here. So this was from a 1960 spacecraft, and it was one of the first detections of lightning, if you like, from space. That it was the University of Iowa. I think it was something like 1963. And you get these signals and they're called whistlers for reasons that should become obvious when you hear them.
Earth whistlers.
So that's these whistlers, which you can use to detect lightning in space. And there are other magnetic signals that lightning and charged particles produce, which I'll touch on a little bit later. So just bringing that part together a bit, if you want to detect lightning on other planets, there are several ways you can do it. There's sort of families of approaches. You can look for the light from lightning, or you can listen to its like electrical and magnetic signals, or you can listen to the sounds from lightning. From thunder. If you're on Earth, you can look with a telescope, or you can use a radio telescope to detect the electromagnetic signals. If you're in space, you've got a spacecraft, you can have a camera, it can have a filter, as I said, or you can use radio receivers or magnetometers. And if you're inside the planet's atmosphere, you can look for lightning. Normally, when I say transients, that's the sort of fluctuation. Or you can use a radio, or you can measure the electric field. And of course, you can measure thunder, as I was just saying, for which you need a microphone. That doesn't work outside. That doesn't work outside the atmosphere you're in because the sound can't travel. How do you detect lightning? And I've been talking about how you detect lightning, but if you go to another planet with a spacecraft or you're on Earth and you say, hey, I found lightning, what actually counts as being good enough as lightning detection? And that's not always straightforward. And there are quite a lot of arguments about what constitutes detection. Some people say, oh, I've detected lightning on Venus, but other people don't believe them because they've only got kind of one set of data that has looked at potentially what the lightning signal is. I think probably for lightning to be detected, you probably need one or two of these at once, and then people really believe you. So if you have a camera and then a radio receiver on the spacecraft, and the camera sees a flash, and at the same time you get a wobble in the radio receiver, people would believe that. But if you just had a camera, people might go, oh no, it was something else. So that's why lightning detection isn't as straightforward as you might think. You think sitting here looking at a thunderstorm, it's not difficult to detect lightning, but it can be a bit harder than that. So extraterrestrial lightning, as I was just saying, so the first extraterrestrial lightning was detected at Jupiter by the Voyager 1 mission in 1979, and it's been detected very many times after that. There have been quite a few space missions to Jupiter, and they've all seen lightning, all the ones with a camera. And the picture on the right is the first picture of the lightning. So you can see these flashes here. This is just a camera. It didn't have a filter. It's just what they call a broadband camera. And then actually at the same time, they got a double win. They detected aurora on another planet at the same time as lightning. So that's some very nice pictures. They also detected whistlers. I was just saying that people might not have been convinced if they just said those bits of light, they're lightning, but they had whistlers as well. So that was really definitely lightning. The lightning storms on Jupiter are very, very energetic. They're about at least 1,000 times more energetic than lightning on Earth, which is quite energetic. But there are still some things we don't understand. The radio signals don't get out as well as we think they might, which is a bit weird. So it's been quite hard to detect the radio signals of lightning from Jupiter. And very recently, in the last couple of years, there's been a new type of lightning detected, which is to do with lightning from clouds made of ammonia, not water. So previously, the lightning clouds on Jupiter, people think they're just the same as Earth thunderclouds, because we can measure in different ways that there's water clouds and ice clouds. And so the lightning comes from a place where the thunderclouds are. So it kind of makes sense that it would be the same as Earth. But then the Juno NASA mission detected lightning quite high up in the atmosphere, and this wasn't expected. And they think that is generated by ammonia clouds, which is quite exciting to those of us who work on lightning, because it's the first time a new type of lightning has been discovered in space, if you like. We see lightning dust and we see lightning in sort of thunder type clouds, but this was a new type. And just to show you how much space technology has come on in these sort of 40 or so years. So this is the Juno NASA mission. It's got some really lovely pictures. You can Google for them. I haven't been able to show them today. Lovely weather pictures in Jupiter showing all its clouds and swirls and the Great Red Spot. They're really attractive. But the star tracker is an engineering camera that is used on the spacecraft, and it is used for navigation. So it points at a star. So it's not as good quality as the science cameras. But nevertheless, this star tracker camera has picked up the aurora and lightning. So this is just like a side effect of having the engineering camera, that you can see how much better quality the pictures are in comparison to the best camera they had on Voyager 1 in the 1970s. So these things have really improved a lot. And there are many detections of lightning on Jupiter, and it's used to sort of as a weather indicator for Jupiter and Saturn now. Moving on to Mars, this is a bit different. Mars has lightning, or may have lightning in dust. And Mars is quite windy, and it gets heated up by the sun. Its atmosphere is very thin, so the surface gets hot where the sun's shining on it, and this means the warm air rises and it makes wind. And there's quite a lot of loose, sandy stuff lying around on the surface, and the wind lifts it up. And that means you get a lot of dust storms. And you can see on the left, that's a picture of Mars without a dust storm. And then on the right, there's a picture of it with a dust storm, and it can cover the whole planet. So you can get dust storms that are really big that cover the whole planet, or you get just little small dust storms and dust devils, which are sort of whirling local vortices of dust that are typically a few meters across, can be up to 100 meters, I think the biggest ones. And that's a dust devil on Mars. So they're known to happen on Mars, and they've been photographed and videoed lots of times. And what we know about dust storms and dust devils on Earth is they have electricity in them. And that's because the dust rubs together when it's blowing around, and that makes it become charged up. And I think when there was the Dust Bowl in the United States in the 1930s, there was crackle on people's radios and things from the dust being charged. So it definitely happens, and you can measure the electricity in dust devils, and people do that on Earth. So is there lightning on Mars? Well, the situation is we expect there to be lightning on Mars, but it's never been detected. Why do we expect there to be lightning on Mars? Well, I was just saying that the dust will become electrically charged. And because Mars's atmosphere is much thinner than Earth's, it means it's kind of easier to generate lightning. So if you took a dust devil that the electricity you measured on Earth and plunked it on Mars, it would make lightning, even though it doesn't make lightning on Earth. So we do expect the dust to generate enough electricity for lightning on Mars. Also, there are lab experiments where people shake up dust and in a tank with carbon dioxide in to simulate Mars's atmosphere, and they've seen discharges in those, and they're also modeling like numerical calculations that predict this lightning, but it's not being seen. So we've got to ask, well, why? And then a few possibilities for that. Firstly, if it's in the dust, and this is the bottom right is an artist impression of lightning in a dust devil. It's likely to be fairly, because of the nature of the like in the thundercloud, it's quite big, it's 30 kilometers big, but the dust devil is quite small. So the lightning is going to be relatively faint. And because in a dust cloud, it's going to be difficult to see. Just the light gets scattered around by the dust. And people have tried to look for radio emissions from Earth and also from spacecraft, but they've not really seen anything. So we think it's just in the dust and it's relatively weak, so it might be hard to spot. So really the situation at the moment is that dust, we know the dust is charged because it sticks to things, and you can see on the rover, the wheels have got red dust on them. So this is just like rubbing a balloon on your jumper, it gets charged up and you can stick it to a wall, the dust gets sticky and you can stick it to the spacecraft, but you don't want it to stick to the spacecraft, but it does. And it sticks to the solar panels, which is a problem for Mars missions. So if we want to understand lightning on Mars better, I think we need to go to Mars and measure at the surface or near the surface rather than from an orbiting spacecraft, because the dust is faint, the lightning is faint, you need to be there. And there have been attempts to do this, but Mars missions are quite tricky and quite a few of them have been lost. And sadly, all the ones with relevant instruments on have not worked. And there was going to be one launched this year or last year, but it was sadly in collaboration with the Russians. And due to their antisocial behavior, it's not happening. So there are no missions going to Mars anytime soon, let alone any with these lightning detectors on, which brings me on to some lab work. So I've done some work over the years measuring dust in the lab to try and look for Mars lightning. And we made various rigs that mainly they work on the principle that if you allow some dust or sand or whatever to fall, it rubs together as it falls and it becomes charged up. and you can measure the electrical signal from that dust. And we've refined this over the years. I will show you an early attempt. This was like a rotatable tank, and it was meant to be Mars. So we would suck all the air out and fill it up with Mars gas. And you can see the highly technical cake tin at the bottom, which is used to measure the electricity. We learned to do things on the cheap over the years. So this is trying to do a test. So that was supposed to be a release, a controlled release of Mars analog material, but it was not very controlled. So we moved on from using that now, and then we moved to a slightly more elegant rig, which is, you can see in the picture here, and that's what we've been using. And we did some experiments with volcanic ash as well, because there were the Icelandic volcanoes about 10 years ago, and they made quite a lot of lightning. And this is my colleagues, Isabel and Kerry. I should say it's the only all-female team I've ever worked in, and it was one of the most successful ones. And instead of doing that thing that didn't work very well, we had a better system for dropping the ash through the rig. But it was the same principle. We dropped it and it became charged by rubbing, and then we collected it at the bottom. And we did some tests on these ash, and we found that the volcano that produced more lightning produced a lot more electricity in the lab. So that was good. So we're moving on from that. This is some current work that I'm doing with some students, and this is to do with trying to understand what you would see if you had your spacecraft at Mars. Magnetic field sensors are quite often put on spacecraft. People just put them on because there's lots of interesting things to see. And then people go, oh yeah, we'll detect lightning with this magnetic field instrument. And that's all very well. But then you start to think, well, what would they see? What would it look like? And it turns out they don't really know. And so we've got a project at the moment, which is to do some measurements looking for magnetic signals from charged dust. So we're going to charge up dust, and we already know how to measure the electrical signals due to those previous experiments I just showed you. And we're going to also try and work out how to measure the magnetic fields. And then we're going to be able to apply that to understand and improve spacecraft instruments and data. So there's a little bit of science in this. This is a thing called a solenoid, which is a wire with a spiral. And if you pass a current through your wire in a spiral, it makes a magnetic field. And then that picture, the magnetic field is kind of inside the coil. So it's the coil, if the coil's like this, the magnetic field's going that way or that way inside the coil. And so if we want to try and make a magnetic signal from our charged dust, we kind of want rotational motion. Because previously we just dropped it. So we think the magnetic field is going to be stronger if you get rotation, which is, of course, what we saw in the dust devils. So we know that magnetic fields are made from dust devils on Earth. There's 30 seconds of data from a dust devil on Earth with magnetic fields. So there's quite limited data. So how can we change our lab experiments to do this? Well, if you imagine having your spiral of dust going that way, so we need a way to rotate the dust, basically. So we have a rig which is quite similar to the one I just showed you. It's sort of multi-purpose, so we can drop the ash through, or Mars. We use Mars simulants, which is a copy or a sort of Mars-like dust that you can get on Earth. And we have a kind of paddle, like an ice cream maker or a food processor at the bottom that's supposed to loft the dust. And we've got various other ideas. You can use air as well to blow the dust around. So we're trying to look for these magnetic signals at the moment. It turns out it's quite hard because they're quite weak. So that is ongoing work. And because it seems to be quite difficult to do this in the lab, we're also looking at magnetic field data from a mission that's at Mars at the moment called InSight, which is really a sort of geology mission looking for earthquakes, but it has magnetic field data. And it turns out they can measure dust devils as well, which has been a sort of side part of what they've done. So we're analysing that data. And separately, we're trying to look at the fundamentals of this charging, so the rubbing of particles together, and how does that work? Because it's been known for a long time, but it's not really understood at all. And this is relevant to industry because you have factories with powder, fertilizer factories and that sort of thing. The powder gets charged, and you can And that can be a hazard. You can have fires and things that are triggered by sparks in these factories. So moving on, could Venus have lightning? There's a artist impression there. I think that's a bit fanciful myself. The people have looked for Venus lightning a lot of times, and there were Russian Venera probes in the 1980s, and they were quite successful. Talk a little bit more about that later. And then there have been some recent observations from Venus Express. They're interpreted as whistlers, but they're a bit controversial. And spacecraft that saw lightning easily at Jupiter didn't see it at Venus. So it becomes a question of what's going on. We don't know. And there are a lot of things that aren't known about Venus lightning, like how would the clouds get charged enough? They're not made of water. They're not made of dust. The stuff they're made of isn't obvious how that works. Where would the lightning be? We don't know. So there's a lot not understood. And I'm slightly involved with a Japanese mission, which has a camera. And that's been in orbit in Venus for several years. And so far it's seen one flash, which was there, that red dot. And as I was saying earlier, it's not clear whether that's lightning or not. It might be a meteorite. We don't know. So there's all sorts of unknowns about Venus and lightning. Moving on to the outer edges of the solar system, Voyager 2, my favorite space mission of the 1980s, went to Uranus and Neptune, and it measured radio signals from lightning. Didn't see anything. Interestingly, they were stronger at Uranus than they were at Neptune, despite the fact Uranus got a reputation for being a bit boring from Voyager because it just was featureless, and Neptune had lots of clouds and stuff. So we don't know where the lightning comes from, but there are water ice clouds, so people think it was probably from the water ice clouds. There's a possibility, as I mentioned earlier, that you could detect lightning on Uranus from Earth. And there was a radio telescope that was looking for it, but unfortunately that was in Ukraine, so I'm not sure that's working anymore. Just unfortunately, no aspects of science are immune to politics and war. So moving on to a different type of electricity, which is away from thunderstorms, and this is to do with you get electricity generated in the air all the time from cosmic rays, which are particles that come from space. They're generated by very energetic explosions and exploding stars and that sort of stuff. And they're constantly coming from space down to Earth. And they make a kind of cascade of different particles, tiny subatomic particles, neutrons and protons and stuff, and you can measure them. And you also get ionization. This is sort of at the breakup of the air to make a tiny amount of electricity, nothing like lightning, much smaller, from radioactivity, which is emitted from rocks near the surface, and also from space weather. And this makes ions and electrons, which are tiny charged particles that kind of float around in the air. They're about a few hundred per cubic centimeter at the surface. And then there are more the more you go up, because you're getting nearer to space. So there are more cosmic rays. And they make the air conduct electricity a little bit. So why should we care? They're quite small. Well, basically, they're sticky. They stick to stuff. And this means they can stick to clouds and dust and haze and have possible effects on the weather, perhaps on Earth. On Earth, there's a lot of other things making weather. So the small electrical effects are very tiny and are being researched. Is there anything happening? Probably there is, but it's probably quite small, especially compared to other weather systems. However, the outer planets like Uranus and Neptune, there's not very much sunshine because they're so far away, and that means electricity becomes more important relative to other sources of sort of energy. And an example of this is on Neptune's moon, Triton, which was, I think, discovered by Voyager. There's a very faint cloud of ice, and that is thought to be electrically generated due to these ions, and there's no other explanation for it yet. So all this stuff that we don't understand what encourages us to do measurements and to make instruments to do those measurements. And the ions that are made in Neptune and Uranus, they cluster, and that can make clouds. And that is the same as what happens inside a cloud chamber, which is a tank where you can visualize the tracks of radioactive particles by putting a lot of water vapor in, or alcohol vapor, I think is usually used, and that condenses. We'll just watch that again. So all these are tracks of cosmic rays and natural radioactivity, so you can see them making clouds. And this mechanism doesn't work naturally on Earth, but in the other planets it does. So it makes cloud, and I did some work to show that this mechanism was involved making clouds on Neptune. And I was very pleased to be able to use cosmic ray data from Voyager 2, because that's the first time I'd actually got to use the data for real. And we found a similar effect in the atmosphere of Uranus. And that was the first evidence that two planets, the sort of clouds, are kind of driven by similar effects, and that's linked to the sun. And then over the years, I've worked on quite a lot of different ways to do measurements of these ions. And this is an instrument I've worked on for a long time, the PIMS, Programmable Ion Mobility Spectrometer, which is what I made for my PhD. And the left-hand one shows the PIMS made then. And it was computer controlled. I had a microcontroller in it, which at that time was a big deal. It's not now. And then quite recently, I worked with a company called A Squared Technologies, and we've modernized this. The electronics have become a bit out of date, and obviously the computer control part needed a bit of modernization. So we've improved it in the last year or so. So that's been nice to return to that lately. We can also detect infrared absorption from ions, which I did some experiments on in the lab, and found a particular area, particular wavelength where we can see a signal from ions. And I did some measurements in the atmosphere where we had to make, these things tend to be quite slow because you have to make your own instruments to do it. And we did some measurements and eventually found a signal from ions in the atmosphere after sort of combining a lot of data. So that dip in the graph at the bottom is a signal from ionization in infrared. And I've measured ions in quite a few places. So I have a space weather station at Snowdon Summit, which I've run for quite a while. It's mainly sort of education and outreach now. It's very good to get students to work on different aspects of this. And we had, until the pandemic, we had real-time data on a bilingual website. It slightly fizzled with the pandemic, but I've got a summer intern working on it at the moment. So that is going to be up and running again very soon, I hope. New work. So we have a new instrument called a microscintillator, which measures the radiation that makes ions, these particles. And it's being developed with A Squared Technologies again. I started it at Oxford, which that one's got Oxford branding. It's moved on a little bit since then. And we've done some balloon launches with it. We put it on a weather balloon, and we released the weather balloon, and we can test it. So let's just see this weather balloon launch. This was from quite near Bristol, or Berkeley, which is between Gloucester and Bristol, in 2018. So it goes off into the sky. Normally, you don't get it back, which is why it's good to make these instruments very small and cheap. So on that day, we actually saw some unexpected results, which is interesting. So this graph shows the results. Basically, the yellow bits are sort of what you would expect to see. So it's the energy of particle, and as you go up, there's higher energy particles. The top left corner shows that there are some low energy particles very high up at the top of the atmosphere, and these were completely unexpected. We weren't looking for them at all, and they took some explaining. And it turns out they're from space weather. And then very fortunately for that exact same launch that I just showed you the video of, there was a satellite overhead at the same time. So we were able to look at the satellite data and look at the balloon data and show that they agreed. And the balloon data was from 30 kilometers up, and the satellite data was from 750 kilometers, but they were measuring more or less the same thing. So this is work that's ongoing at the moment, and we're developing this instrument to put it on more balloons and maybe also send it to space. Just a little side part, more fun with ionization. So this is an engineering department, and it's not just about measuring stuff that occurs naturally. It's actually about making things and making things better. And I've done some work on ion thrusters for spacecraft propulsion. So the same science is underneath it. And you can make ions in a spacecraft and emit them. That will push the spacecraft forward. I have a PhD student working on that at the moment. It's been nice to return to that work since I've been at Bristol. I worked on it in my job at the Rutherford lab, and I'm coming back to it. And some types of ion thruster need an extra part which emits opposite sign of charges. Otherwise, if you have too much charge building up of one sign on a spacecraft, it's bad. And we worked on a thing called a neutralizer to keep the spacecraft neutral. And it turns out it may be possible to use ions in air for propulsion as well. There's a paper from MIT where they've made a plane that works on ions quite recently. So that is something I'm interested in developing. Just coming to the final part now. So moving electricity around planets. So these ions and the lightning together can make a thing called an electrical circuit. So like a battery and a wire, if you like, in the atmosphere. And that is called the global electric circuit. And it was actually suggested by a scientist called C.T.R. Wilson, who became famous for inventing the cloud chamber in the 1920s. But he has a Twitter feed from beyond the grave. He was famous for inventing the cloud chamber, but he turned out he was actually obsessed with the weather. He's really famous in particle physics and he got the Nobel Prize, but he spent his whole career working on weather and atmospheric electricity. And so he hasn't had much credit for that. So we're trying to redress that now. And you may have these global electric circuits on other planets. And a student, sadly not me, in the 1990s suggested that in their undergraduate dissertation. So this is important because it links the top and the bottom of the atmosphere. It means there's current flowing all the time, even away from thunderstorms. So it's everywhere. Electricity is everywhere in the atmosphere, and this flow of current has small effects on the weather. And you can say what is needed to have this circuit in an atmosphere. You need to have lightning and you need to have a conducting layer at the top and the bottom. So we can look and see if there are global electric circuits on other planets. And that means there's certain things that will happen when you know there's a global circuit, you know stuff will be going on. And it seems that Mars and Venus, if there's lightning there, probably have global circuits, but the other planets, not so much. And this is an example of the Mars global circuit that someone came up with. So the dust storm is like the thunderstorm on Earth, and then you get current flow around the atmosphere. Just sparks on Venus. So the Venera spacecraft, the Soviet mission, and they landed at Venus and they actually survived for a few hours. The surface of Venus is really horrible. It's like 400 degrees C and 400 bars. It's really high pressure, so everything gets squashed. But the sensors worked and they provided some interesting electrical data. This is a model of the Venera spacecraft. So we've been doing some work on this recently to learn about the electrical environment on Venus. It's quite tricky. You have to try and exploit what data you have. So we've done two different types of model. Had an undergrad student look at an engineering model of the Venera spacecraft. And he's looked at where the instrument might have been. Because it's Soviet, there's not a great deal of literature. And people were quite cagey about what they were up to in those days anyway. So it's quite hard to know. So we've been trying to deduce where this instrument might have sat so we can understand what it saw. And there's also a PhD student who's looking at a different type of model of the atmosphere. And it turns out you only really get sensible results if there's this global circuit on Venus. You can see in the bottom right-hand plot, those two lines agree, and that you have to make certain assumptions, and they only agree, the real data and the model only agree if you have this circuit on Venus. And that basically means there might be lightning on Venus. So it would be an alternative approach to detecting lightning on Venus. And as you remember, I was saying that lightning on Venus is quite controversial. So this is a new thing that we're working on. So just to try and bring together all the planets that I've gone on about and what is going on. So it seems lightning's quite common in the planets. If there's a solid lightning spark, that means there's definitely lightning. And if it's grayed out, it means we're not sure. And is there a global circuit? So the more rocky, solid planets and moons tend to have global circuits or could have global circuits compared to the gas planets. So if you want a kind of takeaway message, electricity has been everywhere, always in Earth's atmosphere, and is also other planets. And lightning is one of our oldest natural hazards, and it's out there in space. And there's a lot going on, and it's going to keep scientists and engineers on their toes for a long time. And it's also being used to sell chocolate, as well as sparking life itself. And even Reading bus shelters. I spotted this is near my house in Reading. And there is a Mars, recharge on Mars, it says. So yeah, atmospheric electricity is everywhere, and planetary atmospheric electricity. So that's pretty much it. I just want to acknowledge lots of people and funders. I'm sorry if I work with you and I've forgotten to put you on. I did try and include everyone I could think of. So thank you very much. It's been a pleasure to speak to you today.
So, Karen, thank you very much. Absolutely wonderful lecture, full of loads of interesting ideas and concepts there. Fossilized lightning. Did lightning start life? Dust storms and dust devils on Mars. Double bass playing. Cake tins full of Mars gas, perhaps, at one point there. Ion thrusters and galactic cosmic rays. Fantastic. I loved every minute of it. Thank you very much. So we can go into some Q&A now, if that's okay. And I also need to have a look at this laptop in case there's any questions coming in online. Not just yet. I'll look over to you in a moment. So who wants to kick us off with a first question? Anybody? Yeah, okay.
My name is Bobby and I'm really happy to be here. Thank you so much for your lecture. I really enjoyed all that. I especially enjoyed when you got your cello out and was talking about the relationship between the music and the weather. I was maybe expecting to give us a little bit of Four Seasons by the Baldwin. But really fascinating stuff. And in terms of these global electric circuits, and just the sheer amount of lightning that we could see going on just in a short period from that satellite imagery. Is there any realistic work, theoretical, most likely practical and engineering challenges probably put it many years ahead, but in terms of actually harnessing any of the electricity within the atmosphere for commercial purposes, and were that theoretically possible, what accessing that power source might actually do in terms of any kind of like potential disruption of the other effects that circuit has.
That's a good question. I think the thing about harnessing it is the currents that flow in the global circuit are very small. And then the power is what you want if you want electricity, which is current times voltage. And the currents are quite small. And so it would be really hard to harness that, I think, other than just like covering the planet with some big plate and not collecting much electricity. I mean, people have had ideas about this for a long time, but it seems to be quite practically challenging. I've not really seen anything that I've been massively convinced by that would work. And yeah, lightning maybe, but that's quite hard to collect.
Okay, thank you. Question here.
What happens to the electricity when lightning strikes the ground?
It flows through the ground. It all spreads out and sort of balances, sort of flows away because there's a lot of earth and it just flows through because the ground conducts electricity. It just flows away. It goes away.
Then wouldn't that energy have built up and therefore we would have lots of charge in the earth?
Well, I think, yeah, to some extent, yes. But then there's this circuit that balances it all. So there's a flow of current that balances the lightning. That is what the global circuit is, basically, yeah.
That was very interesting, thank you. We're on the verge of all sorts of improvements. You know, there's generative AI, there's, I'm sure I saw something about a quantum computer last week that now operates at 70 qubits. Are there any sort of step forward that are going to give you the ability to build much more powerful predictive models, or effectively take a leap forward in terms of your ability to predict and detect lightning or electricity?
Yeah, that's also a good question. I think that satellite detection is quite, I mean, that's quite a big step forward and that's quite recent. And I think we're just starting to look at that. And then for other planets, I think lightning cameras and things like the Venus one, I mean, it's still a long way to go, but it needs more work really. So I think that would be good. I'd certainly love to have, personally, I'd love to have, you know, little detectors on landers on every planet. That would be what I would ideally like to have. I don't think that's going to happen very soon, but there will be a few coming along.
Okay, thank you. Any other questions, please, Thea?
When you're looking for lightning on other planets, how much lightning are you looking for? Is it like one strike every day, or is it happening like multiple times so you should do fine?
Yeah, I don't think we really know. We don't know when you go. I mean, for Earth, it's 42 flashes per second. So we've got a kind of rough idea of that. What people do is they try and work out the rate. Once there's an observation, or you know, if you see 2 lightning flashes an hour, you could say there's 1 lightning flash every 30 minutes over this area. That's what people tend to do. So they tend to sort of build up understanding of what's going on. So I think the rate for Jupiter, I don't know if it's quite low, but it's very powerful, even though it seems relatively common. Jupiter's quite big, but if you count how many flashes per second, it's less than on Earth, but they're really powerful. So that's a sort of, you don't know what you're looking for. I mean, you could have a model, you could try and predict it, but that would be hard, and they're not normally right, because we can't even do that for Earth. So you start with what you've got and sort of build up your understanding the more observations you have.
Okay, yeah, please.
Why does the lightning fork spreading out?
I think the current just takes the easiest route. And so occasionally you have you have little channels in the air that are slightly more conductive. So the cosmic rays are coming all the time and ionizing, and they make a little weak channel, and then the lightning just takes whatever route suits it. So it tends to spread out.
Never goes in straight lines then?
There's always, there's a whole lot of lightning science I could go on about at length. So, but yeah, roughly it tends to branch out a bit.
Okay, I've got a couple of questions here online, if that's okay, Karen, just to include the people who join us online. So we've got here a question that says, there are a number of unique lightning phenomena here on Earth, such as the sprite and jet. Do these happen on other planets as well? Any chance of detecting them?
Yeah, people have predicted them to happen on other planets, because that's to do with what gases emit light. You roughly know what gases are there, so you can kind of work out what you might see. It's being predicted for Venus and Mars, I think, and observed on Jupiter quite recently for the first time. There's a paper out in the last year or two suggesting that they're a little bit tentative in the paper, but they saw this upward going lightning. It went with the Juno observations, the mission I was talking about in the talk. So I think, yes, it has been detected at Jupiter. And then for Venus, it's quite interesting because Venus is covered with a very thick layer of cloud. So that's one of the reasons why it's hard to detect lightning on Venus, because it can't get through the cloud. But if you have these upper atmosphere lightning, that would be above the cloud, so it'd be easier to see from space. So people are trying to spot those on Venus, I'm pretty sure.
Okay,
it's not being seen yet.
And for my benefit and perhaps some other people, could you tell us what sprite and jet are a little bit that are in this question? Because I've got no idea, sorry.
I'm looking at people in the audience who know much more than me about this.
Martin, perhaps? I can see Martin there. No comments.
They're discharges, so that it's the same principle. The voltage kind of builds up at the top of the cloud, and then when the breakdown voltage of the top of the atmosphere is exceeded, you get a discharge. But because the atmosphere is very thin, because you're very high up, the gas mix is slightly different, and you get a different coloured glow. That's why sprites are red.
Okay.
And then I don't know what the difference exactly between the jets and elves. There's a whole family of different types. They're all very pretty, but I don't know the details.
Okay, well, if you could hear us there online and you want to explain to us on the chat, let us know. Okay, and we've got another question here that says, what's the state of the art in terms of fast or real-time detection of lightning location and magnitude? I've seen cell towers used amongst the various methods.
Yeah, there's these lightning mapping arrays are quite new, and they can get you have to have multiple stations, and they kind of triangulate the lightning. They're very accurate, predict a very accurate location. They've been used particularly for some really nice volcanic lightning work. So if you have a volcano and you have this system, then you can work out exactly where above the volcano the flashes are happening. I don't know how common they are, whether they're just a kind of research thing, whether there's going to be a whole network of them in due course, I'm not sure. Okay,
thank you. Any other questions in the room? Yeah, please.
Thanks for the really good talk. If I was a supervillain, would it be possible to induce lightning or large-scale lightning on Earth, say if I had a fleet of cargo planes releasing charged dust?
I think some people want to control. I've seen some stuff recently about trying to trigger lightning with a big laser. So if you get you have to kind of preload the cloud. You have to have a thundercloud already. So if you're a supervillain, maybe you can make a thundercloud. And then you have a cloud that's sort of preloaded with electricity. Then you can trigger the lightning. There's been some stuff about doing that with a laser. And I think people have actually done this with rockets. If you trigger a rocket, because it makes a channel for the lightning, so then it's sort of ready to go, and then it just releases the charge. So yeah, there's been some news stories about laser triggered lightning recently.
Great question, thank you. Any further questions? Anybody? Yeah.
Fantastic talk is all a little sort of beyond what not really in the science realm. This is all fascinating stuff. And I was kind of just wondering the effect that both humans and climate change, sort of development of technology, and electricity is everywhere around the world now, whether or not that's had an effect on lightning, whether it's more frequent in the atmosphere, whether or not it's changed from what it used to be.
Yeah, there's a lot of discussion about what the effects of climate change on lightning will be. I think the simplest interpretation is that if it's warmer, the atmosphere can hold more water, and that means there's more energy in the system and that the lightning would be more powerful. But like where, there's a lot of local variation where that happens, and there's all sorts of stuff going on. I think one of the things that's being seen a bit more is you get more lightning near that high latitudes now, because everywhere's warmer. And so places like sort of north of Norway and Finland, I think they're starting to see more lightning just because it's warmer, so they get more thunderclouds.
Thank you. Yeah, please.
Do you know, just off the top of your head, what the most conductive substance is?
No. Metals all conduct pretty well, and it doesn't really matter what metal you have, they all conduct quite well.
Please.
That's a broad question, but so if this lightning and these charges are everywhere on Earth, and we have evolved on Earth, what have been the impact of having these effects constantly around us? For instance, the one that comes to my mind is the Schumann resonance. Maybe we don't. Is it possible that we don't hear it because it would be terrible to always hear that background noise? But maybe is it possible that other animals actually hear it, use it for other purposes?
Yeah, I mean, there's some work being done here in Bristol. Daniel Robert's group in biology department are doing electroreception in animals, and you can talk to him later. That bees can detect electric fields, and that they choose which flowers to go to. And I think it's this idea that everything's evolved with electricity around, and that animals and plants have evolved in this context of a background electric field. So yeah, we're probably used to it. You're right. And there's been various studies about the Schumann resonance effects. Some of them I wouldn't really believe them, but there is a bit slightly more serious work on these low frequency magnetic field effects. So there is a bit of credible work out there saying that yes, it's affected us, but it's been around a long time, so we're all used to it.
Any further questions, anybody? Okay, well, I think we can thank you, Karen, again for a wonderful lecture.